So let's consider the following piecewise function. F of x equals x squared for x less than or equal to 0, rad x, or square root of x, for 0 is less than x is less than 4, and 1/2 x for x greater than or equal to 4. Okay. And our goal here is to create a sketch of what this graph's going to look like. Okay, so I'll color code this. Let's look at the first part of this function, the first piece of this piecewise function. Okay, and like I've advised in the past, let's specify the domain for that. So this is going to happen, this first function, x squared, we're going to graph that for all values of x less than or equal to 0. So what you should do is start picking numbers in this set. So let's plug in 0 first. 0 is a part of it. We take x equals 0 and plug it into x squared. 0 squared is 0. So we know it goes through the point 0, 0. We also know it has to be a solid dot because this domain says less than or equal to 0. All right? It's probably worth plugging in -1 and -2 just to get a sense of the picture. If you plug -1 in there, -1 squared, okay, is 1. So this will go through the point -1, 1. And then -2 squared is 4. Okay? Like I've mentioned before, be careful. I mean, you know how to square things. But if you go typing something like this in your calculator, okay, your calculator is going to give you back -4. And we discussed why. Remember, this would mean do 2 squared first and then negate the result. That's different from this expression. This expression is saying take -2 and multiply it by itself. So -2 times -2 gives back +4. Okay, back to the picture. We can sketch this picture like the following. To be consistent with the domain above, we really should put an arrow on the end because there's no lower bound for x. X is just less than or equal to 0. Okay, here's where things get a little bit interesting. So here's the second function. It's going to be used from x equals 0 to x equals 4 non-inclusively. All right, so I'm going to plug 0 in anyway. And if I plug 0 in, the rad of 0 is 0. So what that means is I'm going to put a hollow dot on 0, 0. Okay? Now, if you don't have the luxury of using a different color pen, it looks like you put a solid dot there, right? You can't see the hollow dot that you created. And that's okay. You don't have to put a hollow dot around a solid dot. Okay? This portion of the graph, this second portion, rad x, does not have a y value when x is 0. But the parabola, the first part of the graph, does. And it happens to be exactly where the hollow dot is. We're going to go out to 4. And if we plug 4 in, the rad of 4 is 2. But that would be a hollow dot. If you're not sure about what happens in between, like this is obviously not a straight line, so you should plug in another number. 1's a good number to pick. Square root of 1 is 1, so it goes through 1, 1. And now you can see the rad x graph has to have some kind of curved downward thing, whatever that means. We'll discuss that later. It actually means the graph is concave down. That's the word for it. Okay. And then lastly, 1/2 x for x greater than or equal to 4. So we plug in 4, half of 4 is 2. So here it is the same little phenomenon. This was a hollow dot before, but now it's going to get filled in because of this last graph, y equals 1/2 x. All right, so then we got 5 and 6. We plug 6 in. That's an easy number. You get 6, 3. And then this graph also goes off forever with an arrow on the end. Okay? What's interesting about this piecewise function, there's no jumps in it. There's no point on this graph where it does something like the following, where you have one section of the graph come along, hollow dot, and then you jump to a different y value, and then the graph continues, maybe something like that. Okay? So it turns out that it's sort of nice when we have a piecewise function that connects up well and doesn't have any of these jumps. All right. So let's consider the function f of x equals the cubed root of x plus 77. And the question is, what's the domain and range of this function? All right. So we have 2 ways to do it. Right? We could draw a graph of this thing on the calculator and take a look at that, or we could try and reason it out algebraically. I'll do it both ways. I'm going to start algebraically, then we'll look at a picture of the graph. Okay? So for domain, you should ask yourself, what numbers am I allowed to take the cube root of? Okay? Now, I'll warn you, because I'm sure some of you are probably thinking about this function. Let's just think about that temporarily. I'm just going to call this g of x. Do these two functions have the same domain? The answer is no, they don't, because in the second function g of x, you have to worry about trying to take the square root of a negative number. Okay, because we only want to get back real answers, no imaginary answers today. So if we were going to think about this for a minute, we'd have to say something, all right, well, x could be greater than or equal to negative 77. Right? That would be the domain of that function. Negative 77, if you were to substitute for x, you get negative 77 plus 77 is 0. The square root of 0 is 0. That would be fine. If I tried to go less than negative 77, like maybe negative 80, for example, I would have the square root of negative 3, which is imaginary. So that's not good. So in this case, our domain is restricted somehow. That's not the case with this problem, because we can take the cube root of negative numbers. For example, the cube root of negative 8 is negative 2. Right? The cube root of negative 125 is negative 5. So the domain here is all real numbers, which you can write two ways. You can write that fancy r I showed you, or you can write negative infinity to infinity. Okay. Now we're going to talk about range. So for range, the question we want to ask is, what kind of numbers can we get back? Right? Can we get back anything? It looks like all real. Maybe you think it's all real numbers. So to sort of try and resolve that, just take this function for a minute. Let's just write y equals cube root of x plus 77. And let's just start thinking about things. Is it possible to get back y equals 0? The answer is yes. What number should we sub in? Negative 77. Negative 77 plus 77 would give me 0. Cube root of 0 is 0. Could we get back a really big y value? Suppose I wanted y to be 100,000. Question is, can you solve that for x? And you can, right? You try and solve this for x, everything's going to be fine. You'll get an x value, cube both sides, subtract 77, and it would work. And as a matter of fact, that would work for any number. If we were to take this function here and solve it for x, we would find that we would have y cubed, mistake there, y cubed minus 77 equals x. Well, this expression here could take on any value, right? There's no restrictions there. There's no value that y couldn't be where I'd have a problem cubing it and subtracting 77. So this kind of tells us that the range is also all reals. Okay? Now, the second way to do this is to look at the graph of the cube root of x. So the graph of our function crosses the x-axis at negative 77, and it looks like this. Okay? So here's how we can look at the graph and figure out domain and range. The question you should ask yourself is, what x values have y values to go with them? And so, you start looking on the x-axis. Does this x value, whatever it is, have a y value? Sure it does. It's right up there. Does this x value have a y value? Sure it does. How about this x value over here? Yep, down here. So you can keep playing that game. Wherever you go on the x-axis, there'll be a y value above or below that goes with it. So that means the domain is all reals. For the range, you ask yourself, what y values does this graph actually reach? Well, you do that a couple ways. One thing you could do is say, all right, let's pick a y value. Suppose I pick this y value. Is there some point on the graph that goes with it? Yeah, look to the left, over here. There's that y value. If I go up here and pick a y value, yep, if I move to the right, eventually this graph is going to come up and hit that. Okay? Someone might say, how do you know it always grows? Well, if I'm taking the cube root of numbers, if I just keep taking the cube root of larger and larger numbers, I'll get larger and larger answers. At no point does it reach like a limiting value. All right? So this will go as high in the y direction as we want. The same reasoning in the negative y direction. If I look over here, this graph's going to continue to decrease as I put more and more negative numbers in for x. All right? So then that also confirms that the range is all real numbers. So let's consider the function p of t equals 1,000 over 1 plus 19 times 0.9 to the t. And we're given a domain in this problem. We're saying we're only going to consider t values that are greater or equal to 0. Okay? So what we're supposed to do is estimate the range of this problem. And just so we're clear, this function is supposed to represent population of rabbits on some island somewhere. Okay. So we're supposed to estimate the range of this thing. Let's talk about how you do it algebraically and then how you would do it graphically. We'll look at it two ways. All right. So first off, if I look at a fraction, the first thing I like to do is try and find out, hey, could this thing ever be 0? So what do you think? Could this ever be 0? The answer is no, because you can't have a fraction equaling 0 unless the numerator equals 0. We think about every fraction we know of that's equal to 0. It has 0 on the top, 0 over 7, 0 over 20, 0 over negative a million, whatever. It has to have 0. This fraction has 1,000 on the numerator, and we can't do anything to that. We can't sub in any value of t and have 1,000 turn into 0. So we know that 0 is not in the range. So a different question might be, okay, what's the smallest y value I can get back? Okay, so let's think about that. Let's look at the fraction 1,000 over 1 plus 19 times 0.9 to the t. Okay? If we're looking for the smallest y value, then what we should ask ourselves is, what do we know about a fraction, or what do we know about fractions, if we want them to be small? If that's a good question. If I want a whole fraction to be small, then basically that means is, let's get our denominator to be as big as possible. Right? Because if our denominator gets as big as possible, right, then I'd be doing 1,000 divided by the biggest possible number, which would give me the smallest answer. And that's what I'm trying to do here. Let's start looking at the denominator by itself. That denominator, 1 plus 19 times 0.9 to the t. Okay, and let's start thinking about the t values, which we're restricted to. T is greater than or equal to 0. So since we're starting at 0, we might as well plug that in. So if t equals 0, we plug that in. We'll get 1 plus 19 times 0.9 to the 0. Okay. Well, 0.9 to the 0 over here is going to be 1. Times 19 is 19, plus 1 is 20. So this equals 20. That would mean our fraction would be 1,000 over 20, which is equal to 50. So we know 50 is in the range. Now the question is that the smallest number in the range, right? Or is that the largest number in the range? So that's what we need to figure out. What to consider. Let's consider another t value. Let's look at t equals 1 for a moment. And if we sub that in, watch what we get. We get 1 plus 19 times 0.9 to the 1. This gives us an answer, or a y value of 8, not a y value, but a denominator of 18.1. Now, if we turn that into a y value by doing 1,000 over 18.1, we get about 55.249. 55.249. I would recommend rounding to the third decimal place. That's sort of what they want you to do on the AP exam next year. Okay, so now what we've seen is that by increasing the t value to 1, we actually get a y value that got bigger. So the question we want to ask ourselves is, does that continue to happen? Right? And the question we need to ask ourselves is this. If we look at this expression, 1 plus 19 times 0.9 to the t, what we're interested in is finding out is what happens as t gets really big. So we can write that this way. As t goes to infinity, that just means that t is becoming a very large positive number. What do you know about 0.9 to a big number power? And this is a popular SAT idea. Yeah, this actually ends up getting very close to 0. If you don't know that, try typing it in your calculator. Do 0.9 to bigger and bigger powers. Like we said, if 0.9 to a big number goes to 0, then 19 times that is also going to head to 0. Okay? And then lastly, if I do 1 plus 19 times 0.9 to a big number, well, we already determined that this part's going to 0, so this sum is becoming 1. So what does that tell me? Well, what that means is our fraction 1 over, or 1,000 over, sorry, 1 plus 19 to the 0.9, gets really close to 1,000 over 1 as x, or not x, I'm sorry, t in this case, gets really large. So that's our range. Our range is going to start at 50. It's going to head towards 1,000. Now, yeah, right. And then the thing you need to remind yourself of is that really this thing never quite makes it to 1,000. And the reason you know that is because this expression never really equals 0. It just gets closer and closer to 0 through very small decimals. Yeah, just this part of it gets close to 0. The whole denominator, that never quite makes it to 1. It gets really close to 1 from above, but it never makes it to 1. So that's how you reason out this range algebraically. It's not an easy thing to do. The range is 50 to 1,000 with 1,000 not included. Here's the other way to look at it. If you take a minute to graph this thing, what you notice is it starts to do the following. And it gets really, really close to y equals 1,000. But it takes a while to get there. You've got to plug in some pretty big values of t. So this is the point 0, 50. And then beyond that, it levels off near 1,000. If you think about this range in the context of the problem, remember this function told me the population of rabbits on some island. Right? So what this means is that the population of rabbits is beginning to level off at 1,000. So it's sort of like a carrying capacity that you might learn about in biology. Just one comment, this graph isn't really completely accurate. It should look more like the following. It should start by curving up and then start to flatten out. This kind of curve is sometimes called a logistic growth curve. Okay. All right. So let's consider this function. The domain you can get quickly. You know that x can't be -1. We write that this way, from -infinity to -1. A parenthesis on -1 means it's not included. Anything larger than that would work. So there's your domain pretty quickly. In terms of range, my advice algebraically is to do this. Write this as y equals, and now solve for x. And what you might find out is you'll get an expression where you can see that y can't equal a particular number. So let's try it. If we want to get x alone, I want to subtract that 3. I get y minus 3 equals 1 over x plus 1. Okay? I'm going to do a nice little algebraic trick here. Well, if I were to flip the right side, take the reciprocal, that's what it would get. I'd get x plus 1. Well, I can't take the reciprocal just to right. To balance this equation, I have to do that on the left. And I get that expression. Okay? If you think about that, that makes sense. If I tell you two numbers are equal, x and y are equal, then they're reciprocals. 1 over x has to equal 1 over y. So those would be fractions with the same denominator and both have a numerator of 1. Okay, let's just subtract 1 and we're finished. So we get 1 over y minus 3 minus 1 equals x. If you quickly look at the expression on the left, you'll notice that y can't equal 3. That's the one number that's not allowed in our range. Okay, because there's no x value you can choose that would give you back a y value of 3. Anything else is possible. So our range in this problem is just -infinity to 3 union 3 to infinity.